Good morning, everyone. It's indeed an honor and pleasure to be with you all this morning. I graduated from this fine university 34 years ago. Time flies. I feel like yesterday I was here. When Dr. Bray called and asked if I'd talk about the future of tall buildings, I was reminded of I'd say a famous quotation that's attributed to Newton, although he actually wasn't the first to say it, but that's another story. But the idea is that I've been able to see a bit further standing on the shoulders of giants. And of course, I certainly feel that way having graduated from this university and working with my colleagues throughout the year. So I use that as a bit of an inspiration for the presentation I'm going to share with you today. So you can see the future standing on top of a tall building. Maybe. Anyway, let's maybe start by looking a little bit at the past and the present. It's informative to look at kind of the road we've traveled, to maybe look at the trajectory ahead. And to that end, we've traveled a great distance in a very short period of time. It wasn't so long ago that our buildings were very modest. Yet today, we're working on buildings that are really reaching well beyond anything we imagined. In fact, I'm going to break an NDA right now, but I worked on a building last year that's 1 mile tall. 1 mile, not 1 kilometer, 1 mile tall. Whether it's built or not is another story, but we're clearly advancing our practice and reaching for the clouds, if you will. But many of our methodologies that we continue to use today in the design office are rooted back in this day. The code framework, by and large, that we still practice with today around seismic engineering, wind engineering, fire engineering, everything that drives the performance of a structure is rooted in this day, even though our tools have advanced and maybe we think we're smarter because we have some experience. The framework in which we operate is still pretty rudimentary. Now then it was a necessity because the tools didn't exist, and so the structures that were conceived, designed, and built were fairly simple, and were able to track load paths and understand behavior. We started to get a little bit more ambitious and started experimenting with tools and or with materials, advanced materials and composite construction, trying to organize the parts and pieces in a little bit more exotic fashion. But the fundamentals, the load paths, and how the building worked as a whole was still fairly basic. In fact, you could do the calculations by hand with no computer. We started to push further and further exotic materials to the point where we needed to add other things like damping systems because the buildings were getting very flexible and we needed to supplement the strength and the stiffness of the building with some mechanical means. And so we're advancing, but yet we're still working in this framework that's actually pretty archaic. Even today, with some of the buildings that we're designing and building are still in that framework. Now, about 25 years ago, we started to embark upon this journey of performance-based seismic engineering for buildings. We stole from the renovation crowd. The performance-based framework had already been imagined for seismic retrofit and renovation, and we borrowed it and started applying it to new buildings. Some of the buildings in San Francisco that were designed in the mid-2000s, maybe 15 years ago, were the first to really capture that, but we've moved forward and extended that approach to taller and taller buildings. And these core-based buildings, and in fact this building, which is today, right, the tallest building in the world, right, it is a bearing wall building. Back to the basics. It's a very, very simple engineering diagram. You can almost do the calculation by hand, and the framework with which it was designed, meaning the seismic and wind kind of methodologies, are really rooted back in that 1950s office that I shared with you. Yet today our architects continue to challenge us with unique, very expressive architectural designs, or even wacky forms, where yes, we have a tool, a computer that will allow us to put things in and spit things out, but how confident are we really in what we're looking at? And I think the rest of my presentation is going to tie very well with what Dr. Abrahamson was talking about with regard to the seismic hazard side of the equation, if you call it the demand side. I'm going to talk about the supply side now, where there's equal uncertainty, and how do we best manage that uncertainty. So we're designing very heroic buildings today, things that like leap over railroad tracks in a single bound. Buildings that are so tall and so slender they couldn't even really been imagined a few years ago, using tricks, but still in the same basic framework. So when we look in the crystal ball and we look forward, what kinds of things do I see in the near term and maybe a little bit further out? One thing for certain is that cash is king. In my business, the people who pay for the building stock, the owners, the developers, even the institutions who pay for the buildings, care about money. We all are here to talk about resiliency. So how do we change that? And I'm reminded of the commercial for Kona beer. Maybe you've seen the Kona beer commercial. They coined the phrase FOMO, right? FOMO, fear of missing out. That's the resiliency conversation we have to have with our clients, that when the hazard occurs, the earthquake, the tsunami, the tornado, the thunderstorm, or what have you, that damages your building to the extent that you can't use it anymore, but your competition's still in business, that's the fear of missing out. That's the money. Because I can no longer make money because I'm on the sideline. So cash is king. It's not going to change no matter how much we want it to change. We have to change the dialogue to make people understand what's at risk. And this goes back to what Norm was talking about, the risk side and the risk evaluation. So putting it in the world of seismic engineering for a moment, performance-based seismic design has advanced a whole bunch in 25 years. I worked on my very first performance-based design building in 1995. Here we are, 2020, 25 years later, and we've learned a lot. And the practice has, I wouldn't say been perfected by any means, but we've learned a lot and we're better at it. We're more thoughtful in our modeling and our predictions. But let's not get too cocky, because we really don't know what we don't know. We have the ability, I showed in this slide, to these very elaborate three-dimensional models, soil structure interaction models. Very elaborate, but do we have any benchmark against which to reference the result? Do we really know what we're looking at? We know to ask the question. We have a tool that will allow us to maybe interrogate it, but do we really know what we're looking at the end? And that's where the kind of engineering judgment and skill comes in at the moment. But hopefully going forward, we look at these things more critically. The other thing I'll say about performance-based design, is intended to get directly at science, through science and physics, a best estimate of performance of the building. Where we've gone in 25 years is from kind of a open palette of thought and dialogue and science and math to a very prescriptive methodology. It's almost gotten to be too far, where today the performance-based design of many buildings is nothing more than an enhanced prescriptive design. And I think we got to be careful about getting in our own way in that regard. Now, the number one thing I think that we can do to improve the building stock as it relates to resiliency, community resiliency, individual building resiliency, is the demise of R. The one-size-fits-all simplified approach to seismic engineering served its purpose in its time, but that's all it was. It was a tool to simplify a very complicated situation, and if there's kind of the uncertainty on the supply side of the equation, it's all in R, because structural engineers apply R blindly to all kinds of systems that aren't really reflective of what's underlying the science. So I'm kind of a little bit on a soapbox here, but the reality of it is our code today has a reliability framework as its basis. This is in chapter 1 of ASCE 7, the reliability table. If we're able to get at that from the supply side directly through science and math, including consideration of the uncertainty, we will improve the building stock an order of magnitude beyond where we're at. So this marries up completely with what Norm was saying on the demand side. We need to marry the supply side. Oh, right. God, Ron, that's hard. Yes, it's hard. We're dealing with people's lives, though, right? And people's livelihood and their safety. Let's not take it and make it easy. Oh, it's going to cost a lot of money. Yes, it's going to cost a lot of money. Let's raise our fees. Let's get paid to do proper work, to provide proper safety and resiliency for our communities. All right, soapbox. We've got some very ambitious projects going on in our office, in other offices. We need that sort of framework and approach going forward to realize these more exotic designs in a thoughtful and a reliable way. Turning from seismic engineering for a moment, but I'll loop it back. Wind engineering. Today, in my practice, in the practice of tall buildings around the world, this is the great new frontier. What do I mean by that? We have these tools to allow us to interrogate tall buildings and their response to wind. In fact, there recently, last year, was published this guideline by ASCE to talk about performance-based design for wind. Why is that even an issue or relevant? So here's two buildings, Salesforce Tower you're familiar with, One Brickell City Center in Miami. They're both 1,000 feet tall, similar in size, similar, not quite in shape, but in mass. Today, these are the demands on those buildings. The blue line is the risk category 3 overturning moment for Salesforce Tower. The red line is the risk category 3 wind demand for that building in Miami. Wildly incongruent. The building in Miami must remain elastic in our current code environment under those demand levels. It is 5 times stronger than Salesforce Tower. To me, that's absurd. In terms of sustainability, we could build 5 Salesforce Towers with the same amount of material we're going to put into this building in Miami. Is that sustainable? If only we allow some modest nonlinear response, not crazy nonlinear response, but modest nonlinear response in these tall buildings, absorb some of that energy, we can take some of the air out of the balloon. Closer to home in Seattle, this building's 900 feet tall. A little bit more complicated graph. The dashed line you see is the predicted MCE overturning demand on the building. The orange colored line is the wind demand on that building. The green line is the code risk category 3 DBE overturning moment. You see here we have an effective R in this building of about 1.5. It's driven by wind. Why is that important? It flies straight in the face of our notion in seismic engineering of wanting to absorb energy and dissipate energy through nonlinear behavior. We needed to make the building twice as strong due to the wind demands needing to be responded to elastically than we would have otherwise made it if we were only considering seismic effects. These need to be brought together, and that's what that ASCE document is attempting to do. So a big area of kind of new practice for structural engineers in looking at the nonlinear response of buildings subjected to wind load. All right, let's move materials for a moment. Lots of people hear about heavy timber design these days. It's kind of all the rage. It's presented in many ways, from sustainability to kind of the aesthetic of it, however you want to construe it. There are some very, very important questions with regard to seismic engineering that are unanswered. And I'm very fearful in the engineering community that we're kind of blindly proceeding, designing these buildings with kind of an inappropriate approach. I'll give you an example. The diaphragm design for these buildings many times is a nailed plywood diaphragm. And if the floor is 100 feet by 200 feet, the way engineers are approaching it today, the diaphragm design is viewed much as if it was a slab on metal deck in terms of the strength calculation. Nobody's talking about the deformation of a nailed plywood diaphragm that's 200 feet long. And I fear things like the garage and the Northridge earthquake. These sorts of questions need to be answered through research, through numerical modeling, through some pairing of that, not even being questioned at the moment. We're just blindly doing these things. Another topic, right, is we're building these buildings and we're basically harvesting the forest and we're using the wood that we're given. And we know from our designs that the elastic modulus is what controls the design of these heavy timber buildings. Why aren't we growing forests with a better modulus? Sounds a little funny, but we genetically engineer all kinds of crops. Why aren't we growing proper trees to build proper buildings? Our buildings would be much better. It's an interesting question for kind of some dialogue perhaps from the engineering community and the genetic engineering community. Or forget about timber altogether. Let's use a different fibrous material. How about bamboo? It takes 40 years to grow a forest. It takes 5 years to grow a bamboo crop. And bamboo is twice as strong and twice as stiff. Maybe we should make things out of bamboo. But there's a huge amount of research that needs to go on to inform how that actually behaves when subjected to the dynamic loading. Another area where structural engineering and fire engineering and seismic engineering can come together here in fire engineering, performance-based structural fire engineering. To date, fire engineering is very prescriptive. It's really about 100 years old in terms of what's in the building code. We do have the capabilities to test and model thermal heat transfer. We know and can model the heating and cooling cycles of buildings. But at the moment, structural engineers mostly today give it the stiff arm because it's not been our kind of in our body of work, in our practice. In my view, it's just another load case. Yeah, it's a complex load case, but why don't we consider it another load case? And if we do, one of the implications of that is if we strengthen the end connections a little, or if we change the framing slightly, we can do two things. We can have a better fire performance in our building, and we can have better seismic or wind response because the overall system integrity is better. There's more resiliency in the building as a whole, and we've satisfied seismic and or wind and or fire as a collective. So that's an area of improvement coming forward that we're working on now as well. Some of the work that's going on in artificial intelligence to mine huge data sets and to do more predictive work on giant data sets. Again, Norm talked about big sets of data that are growing ever larger every day. Our ability to understand that data and then mine it and use it somehow to predict future events is certainly something we see people working on, but it's going to gain some velocity. Virtual reality we're already using. It allows us to actually enter our buildings before they're ever built and look at various conditions, walk around the floor plate before the contractor actually has to build it. This is very useful when we deal with complicated geometries. And then when the contractor says something we don't like, we can run. One of the biggest things we hear in the construction community is the shortage of skilled labor. So robotics in the field is coming. Seems a little bit pie in the sky here, but it's not so far away that due to the labor shortage, there'll be a lot more robotics in the field in order to build our buildings, and that'll influence the componentry of how we actually make the buildings. Modular construction you've heard about and seen, it's not really caught on people have been talking about it for 40 years, and it's really not anywhere. It's starting to get some traction to go from, instead of this large scale modularity, to more componentry modularity, where you can more easily fabricate and ship the pieces and then put them together readily in the field. And then maybe lastly, research. What I mean and what I want to highlight here is a stronger and more robust connection between the practicing community and the research community. In my career, it's been pretty disjointed, and I've worked really hard on my side to connect that. I think as the practicing engineering profession, if we as a group of engineers came to the research community with more questions and more demands, we want this, please make it so, tell us how, we would be better off. Instead, mostly what we do is let all the smart researchers kind of grasp around a little bit, and then we comment on it. And it's not really all that productive. It's better if we were more marching kind of hand in glove together and telling researchers and the research community what we're aiming for, what we hope to achieve, and then get in the lab and then demonstrate those things. For instance, here there's some link beam testing going on to look at nonlinear wind response of link beams. It's a very important thing. There's a big, huge gap in research on modest yield cycles, meaning yield demands that are strain demands that are 1.5, 2 times yield strain with hundreds or even thousands of cycles. So we're somewhere between the seismic load protocol and the bridge loading protocol, where you're looking at tens of thousands of cycles at a fraction of yield. We need to close the gap in order to inform the wind engineering. To wrap it up, these are the kinds of things that show up on my desk every day from architects all around the world, wackier and wackier and wackier by the moment. What I have is a very optimistic view that we're going to be able to take some of the old framework in the very near future and kind of move past it and get into this more predictive, reliability-based design, looking at measuring the risks and the uncertainties and predicting the reliability of the outcome. And we're going to make incredible skylines even more incredible. Thank you.